Okay, I think we can start. Welcome everybody to the Day of Light. Now, before the first talk, we want to have a brief introduction on who we are as Pulse student chapter and who are the organizations that contributed on organizing this event. So Pulse is actually an acronym for Padova University Light Scientists and Engineers. We are a student chapter, which means that we are a group of students that gathered and plans events during the year, and especially regarding the science of light, so everything that regards light. You can contact us at pulse.unipd@gmail.com if you want to contribute with the organization of these events. We are mainly supported by two organizations. There are Optica and SPIE, as you can see here and there. And we are mainly, even though this year we have also some new entries from master and bachelor students, we are mainly three, let's say, research groups, because we are mostly PhD students. So we are the Photonics and Electromagnetics group, the ACME group, there is regarding optoelectronics, micro and optoelectronics, and quantum future, that is regarding, of course, quantum related stuff. If you want to have a thesis, maybe with us, if you're interested, we can have some collaborations, and so you can contact us at the end of this meeting. So the contributors are Optica and SPIE. Optica is a society dedicated to promoting the generation, application, and dissemination of the knowledge in the field of advancing optics, photonics, and all the science of light. SPIE is a society for optics and photonics. And then this year, we also have some new sponsors, the Società Italiana di Fisica, that aims at protecting the study and the progress of physics in Italy. And then the Società Italiana di Ottica e Fotonica, that has a particular attention on the optics and photonics field, let's say. Here you can see some of the main, let's say, contributors to the Optica Society. It has many opportunities like scholarships and student prizes, travel grants, school and training programs, webinars, networking, etc., etc. SPIE equally has some student scholarships, career center, courses and group training, conference support, and networking. If you want, we can discuss this privately, but mainly it's just to give you an idea of who we're dealing with. As Pulse, we promote different events during the year. Last year, these were some of the events that we promoted. As you can see, we have the Day of Light that basically repeats every year since, I mean, we have here Leonardo, the first speakers. Yes, exactly. So it's been a constant through the years. And here we have Noah that will talk more about it. So I'll give the ground floor.
Thank you, Alberto. So why are we here today? Well, of course, the event is to celebrate the Day of Light, but it's actually the International Day of Light. So it's not exclusive to us. It's not our idea. And we've organized this event in the last at least couple of years, as you can see from our previous flyers. And the International Day of Light is a UNESCO effort to celebrate light in all its contributions to mankind, whether it be in culture, arts, education, science, medicine, technology, industry, and so on. And yeah, well, this basically is the reason why UNESCO sponsors and promotes these kind of independent initiatives, which can take many different forms, as we are doing today, for example. And Yeah, I mean, that's it. I mean, light is extremely important for all the reasons I mentioned before, but why is it on May 16th? Well, May 16th is actually the anniversary of the first successful operation of a laser, which many people, okay, might actually know what it is, but they don't fully understand it. And that also gives a bit of a feeling of why it's so important to keep on let's say, keep on teaching, keep on explaining, keep on showing people, and keep on talking about light-related topics and how they affect the human experience, let's say. So it's a central part of human life and science and technology and so on. And light is everywhere, even if we don't know about it or we don't see it. So with this, I want to show you just a picture of last year's event. And hopefully in a few minutes, we will actually take a new picture for next year. So with this, I thank you all for being here. And I think we can kick off the presentation. And yeah, as you can see, if you want to join us or even just have some questions, please contact us. We don't bite, and we're happy to speak with whoever. So thank you very much again.
Okay. Good morning, everyone. I'm pleased to introduce our first speaker, Leonardo Marcon. He pursued his doctoral studies in optical sensing here at the University of Padova as part of the Photonics and Electromagnetics group, conducting research with the University of Alcalá in Spain and CERN. He subsequently joined CERN as a senior fellow, where he specialized as a test developer for radiation-hard optoelectronic devices. Now he's currently working in Zurich at Coherent Laser Enterprise as a test developer for photonic devices. Please join me in welcoming Leonardo Marcon.
So, hello everyone. Let me find a position where I'm not covering the slides. Probably here is better. Thanks a lot for the very nice introduction. I'm Leo. As you can see from the heavily branded slides, I'm working for Coherent Laser Enterprise. It's a company in Zurich. I will talk about it a bit later on. And here you can also find my email, so feel free to contact me at any point if you have questions or if you want this material or any kind of future reference. Today I'm here to talk about test development for photonic devices. But before starting, let me thank a lot all the organizers of the event, the PULSE, the people from the PULSE chapter from OSA and SPA. I would also like to thank the people from my previous research group, the people from the Photonic and Electromagnetics group here in Padova. And thanks a lot to all the audience who joined today for this very interesting seminar. I'll try my best to make it stimulating and interesting before the first coffee break, but keep up with me for a few minutes now. So my plan for today is not to do a very technical and very theoretical presentation. Today I'm here to talk a bit about photonic devices, why they are important, and to introduce test development in general as an argument, as a subject, and then to provide some real life examples of how to perform test development in the photonic devices field. This is based mostly on my experience, but I will try to find some general concepts, some general topics that can be useful for all of you, and that can be hopefully useful for your future career, for your future decisions. So without further ado, let's start with the introduction. I will now introduce two different environments. One which is 100% industrial, which is my company, Laser Enterprise, and another environment which is 100% research-oriented, which is CERN. And I will try to highlight in both cases why testing is important. So the first thing that I would like to introduce is Laser Enterprise. Laser Enterprise is my company in Zurich, is located in Zurich, is part of Coherent Corp, which is the mother company in the US. And Laser Enterprise is a manufacturing company, which is fairly odd for a company located in Europe, because it's very expensive to grow devices, semiconductor devices in Europe, where most of the production is split between the US and the Southeast Asia. But we still managed to do it, and my company mostly deal with laser sources and photodiodes for different segments. We target the telecommunication segment, so long distance communication, datacom, so data centers for machine learning or any kind of cloud computing, so short haul communication, tens of meters, and consumer electronics, so every kind of devices that all of us use in our daily life. We are, as I mentioned, a production facility, so we have a full production site. We have 4,000 square meters of clean room with the capability of growing semiconductor devices directly on gallium arsenide substrates. We have the capability of processing these wafers, testing these wafers, slicing, dicing, packaging them, and send them for manufacturing in other sites around the world. And what our company sells is not just devices. The goal of my company is to sell the next generation device. So we always try to push in the market the latest development for those specific devices. And this is how we still have a business even while producing in Europe. Because of course, we try to be the first in the market, to have a window of time where we are the only one producing these things. And we offer extremely high quality and extremely high reliability for these devices. And in order to guarantee these three elements, we need to extensively test all of our devices. We need to guarantee that the standards in our production, the testing in our production is done thoroughly. And so in order to do this, we have 150 people dedicated to R&D. And we have a time spent for our devices in our company where 1/3 is dedicated to testing. And that's why test development is considered very important here. The second environment that I would like to present, attenzione alla temperatura, is CERN, the European Organization for Nuclear Research. It is also located in Switzerland, but this time it's in Geneva. In particular, most of the development is done in the Meran site on the border with France. But what is interesting, except for the beautiful place, as you can see, is the image on the upper right side of this slide, which is a representation of the accelerator complex that they've built. This accelerator complex is massive. The LHC, which is the largest range they have, is 27 kilometers long. And as you can see, the accelerator complex is a connection, a very strong interconnection of both circular and linear accelerator, where occasionally, wherever you see a dot or a name, there are experiments located where particles are allowed to collide. And these experiments are used to push the frontier of theoretical physics. CERN as an accelerator complex is not an environment where you would like to walk around while it's operative. It might be slightly radioactive, but it's not as radioactive as you might think of, because any kind of radioactivity outside of the experimental area is a waste. It's wasted energy, it's wasted money, and they don't want that. So under normal conditions, it's almost possible to walk around all of these facilities, except for the experiments where there are higher level of radioactivity, and everything should be fine. But here the key word is should. So in case something is not fine, we need to know soon, and we need to know it in a reliable way. So all the complex, the accelerator complex, is covered in sensors which are required to monitor that everything is going fine. And these sensors generate a huge amount of data that need to be transferred to a control room, a safe control room, where people can operate in order to prevent damages or prevent issues and simply make the situation safe. To carry and to transfer all of this data, we have a lot of, there is an extensive network of optical fibers, and there are a lot of optical transceivers that take care of converting the signals from the sensors into light that then is carried to this control room. And all of these transceivers need to be reliable, full stop. They have to work when the radioactivity level goes high, when the temperature can become harsh, and people need to have trust that the system works when it matters the most, when there is an issue. So also in this case, all the devices that are deployed in the accelerator complex are thoroughly tested before in order to build this trust, this feeling that they will work when they need to. So I talked a lot now about photonic devices, but what is photonics? So here you have anticipated a bit me by introducing a bit photonics before. Photonics is a branch of optics that was born indeed after the Second World War, around the 60s, with the development roughly of the first lasers. And basically it's the science that take care of everything that deals with light and electronics. So generation of light, manipulation of light, and detection of light. Since photonics started, it became one of the core technologies that enabled the acceleration of science that we're still experiencing now. And simple milestones, internet as we know it, based on an extensive network here again of optical fibers and lasers. The machine learning datacom, they will not be possible without optical fibers and network. But there are a lot of fields where photonic devices are core technologies. Here there are non-exhaustive list. But the interesting thing for you, I think, is that photonics is a growing market, and as long as the geopolitics doesn't screw us all, it will keep on growing for the foreseeable future. So it's a very nice field where to be at the moment. It's very stimulating, it's very exciting. And where do we interact with photonic devices in our daily life? So except for particle accelerators, which probably is not an environment that we're familiar with or that we spend time every day, photonics is inside the data centers for cloud computing and machine training. Inside a standard inside a standard data center for machine learning, there are roughly 400,000 lasers installed and photodiode for optoelectronic conversion of electrical signal and data. But once again, I suppose that none of us really spend time in a data center. So we see photonic devices on cars, newer model of cars with self-driving capability or assisted driving capability, heavily employs photonic devices and lasers and lidars to scan the environment, to see without using eyes. And even more, in our house, any kind of devices that has to move around implements photonic devices. And even more close to us, smartphones. If I suppose that any of us has a smartphone, at least one smartphone, and in one smartphone, we're interacting with lasers at least on 3 different points. There are at least 3 lasers installed on any of our smartphone, which are the fingerprints, the proximity sensor, and the autofocus. If you have an iPhone, then you have even another one, a fairly big one in the front screen that scan your face and check your biometrics to unlock the screen. And how do these photonic devices, these lasers, looks like? This is another non-exhaustive image, but this is most the devices that we produce, either at Coherent or at CERN. And you can see here different kind of lasers. So let's start with VCSELs. VCSELs is an acronym that stands for vertical cavity surface emitting light, surface emitting laser, which means that basically on these for these lasers, the light comes out of this hole toward you in the vertical direction. Compare, for instance, to edge-emitting lasers. These are bars because there are several lasers one after the other, where light comes out in the longitudinal direction, so on the floor compared to this screen. The difference between these 2 devices is the application. So datacom lasers, VCSELs, have on average lower performances, but they have a very, very nice feature that is they're extremely small. These are 200 microns by 150 microns. And they're very easy to test because light comes out in the vertical direction. It's readily accessible already when they are built on a wafer. You can just have 2 needles that contact the chips and light will come out of this. Contrary with respect to edge-emitting lasers, where light is emitted in the same direction of the wafer, which means that you cannot really test it. But these bars can emit a lot of power. We're talking about hundreds of watts. They can be used to solder stuff, to weld stuff together, to cut stuff. And they are still not particularly large. This is 0.5 millimeter of length, for instance. If you have your Face ID, if you have an iPhone, this is probably something similar to what is used to scan your face. This is an array of lasers. Each of these dots are single emitters, like these ones. And they basically shine this light in your face with a very small but very bright pulse. And the light is collected back, and they use this to recognize you. And you can see that these devices then are also used inside of optoelectronic devices. This is standard transceivers for optical fiber. You have two main photonic devices here, which is the transmitter optical subassembly and the receiver optical subassembly, where a laser and a photodiode are installed. We will talk about these things later on. And here you have the electronics that convert the electrical signal into light, into modulation. Wafers, I don't know if you already studied them in your career, but basically wafers are disks of semiconductors, normally either silicon or gallium arsenide. In this case, for laser, is gallium arsenide. And the devices are grown on top, and they look roughly like this. This is a 3 inches wafer, so it's roughly these dimensions. There are also bigger wafers that are these dimensions. And each of these wafers for datacom lasers contains roughly 30,000 or 100,000 devices for when they're small. And what is interesting here to introduce a bit, this is the only boring slide, I hope, of today, is the parameter of interest when we're talking about photonic devices. We talked a lot now about testing. And what do we test for these devices? We test everything that is physically related to these components. So we test optical parameters like the optical power or the wavelength. We test electrical parameters to understand how efficient they are, how much power they're dissipating. We test their dynamic behaviors. We want to know how fast we can modulate these devices. And especially for today's presentation, we check their reliability parameters. We check how long they survive in lifetime and how long they survive in an harsh environment, which can be radioactive, which can be at high temperature, which can be extremely dangerous for electrostatic discharges. So now let's dig a bit about what is test development, the main part of this talk. And after giving a general definition and a general understanding of test definition, let's see how this is done for photonic devices. So test development, as you can see in the definition, refers to the science of planning, developing, evaluating, qualifying, and release test setups. This is, if any of you study project management or is somehow related with project management, is basically the same structure of any other project, because indeed test development is the science of developing a project. The difference here is that there are normally much more hardware involved than in other projects. And there are some key differences that I will try to explain while going through the different steps. So in order to start a test development project, the first phase is the planning phase, which is the most important one. The planning phase starts with the question, do we need to do this? Because if we don't need to do this, if we already have a setup that can do this, or if the request that you receive while developing a setup is silly, you don't want to waste neither time nor resources in doing this. Once you agree that it's necessary to do this project, then comes the second question, which is, what are the specifications we're building against? What do you want to measure, and with which accuracy you want to measure this? And this requires a strong interaction with the person who has the idea to develop this setup and with the people who are designing the chip. The geometry of their design need to be reflected in the test setup, and the test setup need to influence the geometry of the device under test. After agreeing on some specifications, then you can move with all the next things, which are understanding which skills are required in order to build a test setup, understand which components can be used to build the test setup, and then finally the boring stuff of preparing a timeline, preparing a budget, and ask for money in order to build it. Once agreed upon all these things, there is a final element, which is understanding which are the output that your test setup need to provide. This is key because everything will be evaluated against the output that it provides. Even if the test setup and the test development will cost a bit more, that's fine as long as the output are good. So after the planning phase, there is the development phase, which is normally the funniest one, because it's literally like going to shopping for very cool devices, then you assemble them, then you test them, then you get cool results, you test against the prototypes, you get a lot of raw data, and you start seeing if everything is working as it should. If it's not working as it should, which is 99% of the case, you go back to the people requesting for this test setup, and you discuss with them about why it's not working as it should, and you have feedback, and you improve your development in order to reach the outcome, the output of the project that you're looking for. And then once the setup is fully developed, you start the evaluation phase. You don't want to save raw data on a database because also space online in a database is a cost. So what you want to save in a database, what you want your setup to give out is not a huge, massive matrix of data. You want just the useful information. And this is done again by discussing with all the people that are involved in the project and understanding what they're looking for. So you squeeze this outcome outside, you save this data in the database. The product owner normally just check these numbers in the database and they say, okay, everything is working well, we can sell this device, or we can release this device, or no, there are some issues. So the next step is qualifying. Qualifying is normally the most boring part of a test development project, but is also as important as planning. Qualifying means making sure that your test setup is robust. Is robust not in the sense that if someone with a hammer comes and smashes it on it, it breaks it, but robust in the sense that if you test the same setup, the same device 5 times, you always get roughly the same results. If you test a device in summer and in winter, it has to give you the same results. If two different people test the same device, they need to obtain the same results. This seems obvious, but it's the hardest thing to do because it will never work. You will see later on in the example that even the simplest project has a lot of variances and a lot of biases introduced in very different positions. Finally, once everything works, then the setup can be released for whatever use it has. You write the work instruction, you give it to the users, and they happily test. So as I mentioned here, there are a lot of interaction with people during the test development project. So it's obvious again to say this, but communication is key. You need to develop your social skills. You need to develop your ability to talk with people, to interact with people, to decide when it's worth fighting for something, when it's not worth fighting for something, when to say yes, when to say no, when to say this is going to be expensive. And the second thing is documentation. Write down everything that you're doing. Write down why you decided to go for one component instead of another. Write down the result of your planning phase, especially the specification that you've agreed upon, the outcome that you want from a test setup. Not because in the future the product owner will come to you and say, I want these other things and you haven't given it to me. But because documentation is also accountability. You'll become accountable for what you promised for, and you don't want to make promises that you cannot keep. So write down everything and make sure that what you're writing down is feasible, and this will make everything smoother. Of course, this is now a general description of test development, and this is not necessarily always how you want to deal with a test development project. because, for instance, there are different goals for industries with respect to a lab research or an academic area. In production, you don't want to build a setup that is complex, that is amazing, and gives a lot of fancy results. You want to build something that is small, really focused on what it has to do, and easy to use, because this will be used 24/7 by some operators, and it needs to be easily maintainable. It will need to be easily exchanged, need to be easily built and easily used. For a research lab, instead, you might instead decide to give up some of the robustness that you get during the qualifying, or some of the robustness in the quality of the data, to get more flexibility. It's much better for an academy lab maybe to have a setup that measure 10 different things, not with the real absolute value, correct absolute value, but enough to give qualitative measurements. So you need to adjust this according to the context. You need to be aware of the context that you're working on, and you need to try to optimize also the resources. Everything comes with a price, including your time, including all the devices and all the hours that you spend to build something. And finally, this is more of a personal note on my side. What I think is really important for everything, not just for test development, but anywhere in any sector, is being curious. If you're curious and you understand what's going on, then you have the chance to perform in the best way possible. This is something that is common for everyone. As long as everyone is curious, all the other skills, so the technical skill, the hard skill, the soft skills, will develop anyway, inevitably. But personally, I think that an academic background, working on a PhD, somehow speeds this up. So gives you the chance to deal much early, much more directly with an environment where you have to become critic, where you have to learn that things are not necessarily hard truth, but are always somehow a general understanding, a general agreement on something. And this speeds up a bit the development of skills that are really useful in any aspect of our life, not just work-related ones. So back to the presentation, why is test developing and testing important? Well, from an industrial point of view, it's obvious. So you want to develop quality devices, because devices of quality are much more well received. You want to reduce cost, and you want to improve the customer satisfaction so that they keep on buying your stuff. But these same elements apply also for other world, like the research world or the academic world, where quality doesn't mean necessarily selling more devices, but means having robust results that you trust to build your models upon, and that will withstand the crash with peer reviewing, with publishing, for instance. Reducing risk and cost doesn't mean, in this case, optimizing the business plan for a research environment, for a lab. It means optimizing resources. If you manage to build a setup that takes some resources, but then enable a lot of research, then you will have in the future a lot of resources that will be freed, because you already built a nice test setup to do other research, to do more stuff. So improving a lot the efficiency of your lab and of your research. And finally, when I talk about customer satisfaction in a industry, in a business, of course, we're talking about external client. But in a research environment where maybe you're not selling devices, customer satisfaction is also your satisfaction. You've built something that is reliable, that helped your research, that helped the research of all the other people in the lab. And this builds trust in yourself. And this is something that then you can spend wherever it happens in your life. Of course, this is not easy. And in all environments, also in the industrial one, in the end, there are still open questions. Like, for instance, as a brain teaser, how do you measure absolute values? How do you know if a customer comes to you and asks you to measure the optical power of lasers? how can you reply the output power of my laser is X? And be sure, be confident that this is actually X. It's trivial as a question, and it's an absolute nightmare to answer this, because direct experience, you get the best calibrated device in the market, you measure as accurately as possible that device, you get one result, then you get the same device from the same manufacturer, but different serial number, you perform the same measurement, it is 5% off with respect to the other one. And so which one of the two is the real answer? Which one is the one that you rely upon? And why the two identical devices measure two different things? So all of these questions remains open, and all of these questions makes also the industry environment still very stimulating for someone with an academic background. So let's move now to the final part of this talk. I hope that I'm still in time. And let's show a couple of examples, of real-life examples. This is a project development that we've done in Coherent, so in my current company. We had some customers, some internal customers. This was an R&D group that came to us and said, we would like to measure these devices. These are Datacom lasers, and they come inside a TO46 packaging, which is this packaging that you see here. We would like to measure the LIV curves, which stands for optical power and chip voltage as a function of the current flowing through the laser, and the spectrum of this laser. These are fairly standard requests. But what they wanted is to measure them over a very broad temperature range, up to 150 degrees. And also they wanted the results to be calibrated and qualified, which means that not only they wanted to measure absolute values as close as possible to the real value, but they also wanted this to be qualified. They wanted a certificate that guaranteed that the outcomes were what they were expecting. So the first thing that we did, as I mentioned during the previous slides, was sit down, agree that this was a good idea for a project because we had no setups measuring up to 150 degrees. Write down the specifications, check that we could realize all of this, give a timeline, give a budget, and start working on a proposed solution. And normally the proposed solution is a slide like this, done in PowerPoint with very simple boxes, where you write down all the components that you think are the best one for the job. In this case, we wanted qualified devices and calibrated devices and qualified results. So we went for companies that were already offering a certificate of calibration and a certificate of qualification, which are, for instance, for the source measure unit, Keithley, for a tech controller, the Arroyo ones. And on the measurement side, the Newport integrating sphere and power meter and the Yokogawa OSA. You start thinking about all of this, you start thinking about how will the device be moved between the different measurement elements, how the connection with the sources will be, because everything comes into the quality of your results. The length of your connection, how you place the cables on the table, if there is metal under it. So you have to consider a lot of things. And it's normally worth to spend 20% more also to buy good devices instead of trying to save and get shitty devices, because then you're going to pay that with time after all, and you're very expensive as time. And then you ask someone in your company to prepare a CAD model of the results of the proposed solution, because this helps you understand the geometry of your test setup, the space occupation that it will have, and it helps you optimize the geometry of where to place the devices, where to place the cable, how to shorten a bit the length. Is it comfortable for the user to do this? And also to give an example of how it looked like, because if you do the CAD model properly, then also the truth will be, the real setup will be very, very similar to that. Another very nice outcome of a CAD model is the so-called bill of material. If you prepare the CAD model properly, then your CAD already has all the elements that need to be assembled in the setup. with all the manufacturers, with all the components, all the costs. And if you need to duplicate your setup, it's just a matter of printing that file, go to the market, purchase the elements, assembling them, and that's already done. So after preparing the CAD, you start buying the components, you start assembling your setup, you start optimizing it. For instance, here you can see that we decided to change the lengths used for someone with a larger NA. And you get your prototypes, you get your first raw data. And if everything goes well, then you can move this to its final form, which is in this case, this rack, where you start thinking also about all the other things that are not really technical things, but are very useful. This setup will be used by people, and people like to stand straight in an ergonomic position, have the monitor in front of them, the mouse and the keyboard are an accessible thing. You think about safety. So you put a big red switch in front of them so that if anything goes bad, they can just switch it off and protect their eyes. And then you ask them to start taking this measurement to see if things work as they should. So they start taking measurement. We unfortunately use LabVIEW, but this is again another topic. They start the measurement. They are able to measure these LIV curves. They're able to measure the spectrum. They're able to go up to 150 degrees. So everything is as they want. And so comes the qualification part. So the qualification part, as I mentioned, involves a lot of statistics. So one technique that is normally used to qualify a setup is the so-called GRR. GRR stands for gauge repeatability and reproducibility of your setup, and basically requires 3 different people to perform for 3 times the same measurement on different devices. In this case, we have 9 devices here. We have 3 people doing this measurement 3 times, so they have to spend roughly 1 hour in front of the setup redoing the same thing. Seemed a bit silly for them. But in the end, you get this large amount of results that you can overlap. These are the 9 measurements done by all 3 operators overlap. And you see that overall, with all these nice calibrated and qualified results, they are all overlapping. So it's very nice. You're measuring something fairly reliably. But if you start looking at the statistical part of it, then interesting things comes out. So you get one specific current points, which is relevant for you. In this case, we went for 8 millions. And you see that while all of them measure for the same device, the same optical power, the first users, the first operator, had a much larger variance with respect to the operators 2 and 3. And you start wondering why. Why is there such a clear distinction between the first one and the other 2? What is it doing wrong? Is the setup not working as it should? What's happening? You investigate and you realize that the first operator was following the instructions of measuring device 1, device 2, device 3, device 4, and then starting again device 1, 2, 3, 4. While the other 2 operators decided that to make it faster, they put the first device on and they measured it 3 times. Then they put the second device on and they measure 3 times without moving it, taking it out of the electrical connection and redoing the electrical connection. And this has an impact in your data, which is measurable, which is observable. So the solution here was to specify even better in the work instruction that you always had to remove the device. And in the end, the different statistic, the different deviation was not too bad. We were still able to measure with a 6 sigma GRR, so with a confidence of 99.97% that every measurement we were doing was right within 0.013 milliwatt. But it's a clear example of how important is qualifying. Without qualifying the setup, we would have never spotted this, and we might have had a situation where the measurements were not done properly. So the second example that I'm bringing today is about CERN. As I mentioned, CERN, big accelerator complex, potentially radioactive. A lot of devices around that need to survive a harsh environment. So we need to build trust about these devices. We need to select components that we know will work as they should in harsh environments. So how do you do this? For instance, I was working on the CWDM link project, stands for Coarse Wavelength Division Multiplexing Link. Basically, in the radiation area here, there were 4 transceivers at different wavelengths that were then multiplexed into a single optical fiber going toward a radiation-free zone. And as before, the first thing that we did was sitting down together and agree on the specification of these components, of these transceivers. And in particular here, the interesting thing is the last 2 lines. These were the environmental specification for the radioactivity levels that these devices needed to withstand. So transceivers are fairly expensive components. They can go up to hundreds of bucks per device. So you often don't want to test all the devices during this destructive test, because trust me, you don't want to touch a transceiver after you have irradiated with neutrons and stuff. So you need to understand what is the critical part about these devices. And here again, this stems from being curious. How to optimize the things? The question comes from you, like, why do I'm testing this? Why I'm doing this? Understand what's going on. So we, in the end, understood that the biggest problem for a transceiver was the transmitter optical subassembly, the device, the optoelectronic device where the laser is installed. And in order to understand why radiation was influencing this device so much, we tried to understand from the specifications. We couldn't understand anything. So we literally encased it in epoxy, and we milled it down until we find out how it's done inside. And here you can find some very interesting thing. You see that the laser is here. As I mentioned, these are very small. These are like 4 millimeters. So you can see how small the laser here is, which is focused by a ball lens, which focused the light of the lasers into a ceramic sleeves that then guarantee the mechanical alignment with the fiber. So if you exclude the fiber, there are 3 elements that we know by literature that are sensible to radiation, which is the ceramic sleeve, the ball lens, and the laser. So who would have all of them? And these are the things that we need to test. So how do we do the test? We prepare, once again, a scheme for the test. We agree that these schemes, together with all the people which has experience about this, that this test is right to measure these things. And then we assemble the devices on the test board, and we sacrifice some engineers which will put these devices in front of the neutron source here. No jokes aside, no engineers were harmed in this activity. Here, this is the neutron source. There is the target here, and here are the devices being assembled, and they will go here and being irradiated. As you can see, we're not testing single devices here as well. We're testing a large subset of devices because we need statistics to build trust. Trust and statistics are things that goes together. So we tested the devices from 3 different manufacturers. We tested 20 devices per manufacturer, and we compared the result with an external measurement by a different supplier for their own TOSA, in order to understand if not only we could identify one of the manufacturer which was working as we wanted, but if the results of our own test were in line with what was the common understanding. And in the end, we find out here that manufacturer 1 was making some devices that were in line with the reference one, while the other 2, while behaving roughly the same, had much, much worse performance when irradiated. And so you see, we know how the process works. We know that we found something that behaves as it should behave, but in a much better way with respect to the others. And so we've built some trust. And this is where, in the end, the devices that were installed into the transceivers and are now assembled in the accelerator complex. So with this, I would like to conclude a bit my talk. I hope that I haven't annoyed you, or I hope that it was not too boring for you. So the goal was, on my side today, to introduce a bit different topics that are not really strictly academic, but are relevant somehow in the also in the academic and research environment. Of course, as I mentioned, the most important thing is to understand your context, understand where you are, understand why you're doing these things, because based on that, you can adjust your goals, depending if they are academic or their business. But in the end, the most important part is that you find satisfaction in what you're doing, that you're happy with what you're doing. There are no right choices. There are no wrong choices. So always everything will be important for you in order to maximize your happiness and your satisfaction. So thanks a lot for your attention. And if you have questions, I'm here and I'll try to answer as best as I can.
Do we have any questions?
I'm also available later on in the coffee breaks and for lunch eventually.
Thanks, Leo, for the really great talk.
Thank you very much.
I have some questions that maybe might help some people in deciding about career paths. So at a place like Coherent, would you say that maybe people with master's degrees can apply for positions there? Or would it be better to have a PhD? Would it be better to have some postdoc experience, or can they come right after their degree is completed?
These are very, very good questions, and I'll try to answer based on my experience mostly. So anyone can apply. There are no really, I haven't seen any real blocks for people who do not have an academic background while applying. Normally, having a higher degrees means that you start at a higher position or with better and more competitive salary with respect to someone without the academic background. But overall, this is, I don't see a strong correlation with the performance of the person in his work with or without an academic background. What I notice is that a lot of the performance of someone working depends mostly on its own curiosity, as I was trying to point out during the talk, more than in the art skills or in the other skills that they've developed during their academic background. What I think, though, is that the academic background is very useful in developing this mentality, this approach to problems, this way to think about stuff that is beneficial not only for the work career, but also for their own life and for all their life. So while my company doesn't really care if you have an academic background or not, I will still personally recommend it, also because it's fun to refer to work to do a PhD and to do research, and it will speed up maybe some development or will prove useful for you.
Okay, thank you. And besides like developing one's curiosity, would you have any suggestions for what one would want to maybe focus on during their studies that would help them get a career in coherence? For example, would that include something like more technical skills or internships or publications?
Publication, not so much. Technical skills, much more. Because one of the things that my site, at least in Coherent, does is a personal interview during the hiring process, where they bring you around and they show some of the setups and they ask you questions about how would you deal with this problem or how would you solve that problem. And that is one of the parts that is evaluated during the hiring procedures. So technical skills is definitely something to focus on. Other things that are relevant, no, I think that it's mostly your interpersonal skills, your social skills, and the hard skills. Publication, luckily, in the industry sector is not so important yet.
Thanks.
Any other question? I have more of a curiosity, I would say, knowing you basically. How was the transition? Is that from CERN to Coherent? More from let's say academic kind of like research point of view to more of an industry?
It was much smoother than I was expecting. So I was a bit worried moving from a research environment to an industrial environment, because I heard a lot of discussion, especially in Italy here, about how the industrial environment work. And I can talk about the Swiss environment because I haven't worked in industry in Italy, but it was not so bad. Of course, the speed of development and the goals are much clearer in an industrial setting, are also much smaller. A research environment can afford to focus on multiple things, while in an industry, you're focusing on business mostly. So the goals are clearer and you have to be faster to achieve them. But it's not necessarily all bad, because you also have a faster cycle of work and satisfaction, because you see already the results of what you're doing much quicker normally than in the academic background, than in the academic world.
Any other last minute questions? I don't think so. So we can thank again Leonardo Marcon